There are two major rules of probability, and these should be familiar to you if you took pre-calc, which all of you took pre-calc last year. So you should remember these. So all probabilities need to be between 0 and 1, or between 0% and 100%. A probability of 0 implies that the event is impossible, and a probability of 1 implies the event is certain, right? There is the probability that the sky tomorrow is going to be green with orange and purple polka dots is 0. It is impossible. It is not going to happen. Whereas the probability that the air will contain oxygen in it tomorrow morning is 1. The event is certain. Remember that probabilities are expressions of belief about, are expressions of our belief about outcomes. But I can be pretty certain that the air will contain oxygen tomorrow. And the probability of some event happening plus the probability of that event not happening is equal to 1, right? So we said that the probability of not E, we called that EC, which is the complement of E. And complement with an E, not with an I. So if you rearrange that equation, you subtract P of E from both sides, you're going to get that the probability of not E equals 1 minus the probability of E, which turns out to be a really handy formula, actually. So it's something that you should keep in mind. So, for example, the probability of not getting a queen in a deck of 52 cards is 1 minus the probability of getting a queen. There are 4 out of 52 queens, so the probability of not getting a queen is 48 out of 52. Disjoint outcomes, also called mutually exclusive outcomes, cannot happen at the same time. So, getting a heart and getting a spade in a deck of cards are disjoint outcomes because you can't have a card that's both. The outcome of a single coin toss cannot be both a head and a tail. The student cannot both fail and pass a class at the same time. All right, a single card cannot be an ace or a queen. Ace and a queen. Non-disjoint outcomes can happen at the same time. A student can get an A in stats and an A in English in the same semester. A card can be a queen and a heart, etc. So, if A1 and A2 represent two disjoint outcomes, then the probability that one of them occurs is probability of A1 plus the probability of A2, right? For disjoint outcomes, if we want the probability of one or the other, so this would be A1 union A2, and then we would just add those probabilities together. So, the probability of a jack or a king, that's going to be 4 out of 52 jacks plus 4 out of 52 kings, right? Jack and a king are disjoint because you don't have any cards that are both. Probability of a jack and a red card. A jack or a red card. There are 4 out of 52 jacks and 26 out of 52 red cards. I don't know what happened there. So can you just add the probability of getting a jack and the probability of getting a red card? No. All right, so if you look at a deck of cards, you have 26 out of 52 red cards and 4 out of 52 jacks. If you add those up, you will get 30 out of 52, but that's not the correct probability because you have 2 red jacks that get counted twice. So, the probability of a jack or a red card is the probability of a jack plus the probability of a red card minus the intersection, because that's the part that gets counted twice. Right? So, very important for non-disjoint events that you don't forget to subtract the overlap, otherwise you're going to count that intersection twice, and you are going to get the wrong answer. Right, we can also do this with a two-way table. What is the probability that a randomly sampled student thinks marijuana should be legalized, or they agree with their parents' political views? So, the ones that think that marijuana should be legalized, there's 114 of them. They're the ones that share their parents' political views is 118. So 114 plus 118, but that's an overlap of 78 that get counted twice. So we need to subtract the 78 that get counted twice. Right, so this gives us our general addition rule. The probability of A union B is the probability of A plus the probability of B minus the intersection of the two, because this is the doubles that get counted twice. For disjoint events, the probability of A union B is 0. By definition, that's what disjoint means. They can't both happen at the same time. So, in that case, you can just get rid of that last part because this would equal 0. Probability distribution lists all possible events and the probabilities with which they occur. So, here's a probability distribution for the outcomes of one toss of a coin. Alright, you've got the events, heads or tails, and the probability of each. For a probability distribution, we didn't really talk about this rule before, but the events listed have to be disjoint. And that's implied in this one, the probabilities must total 1. Because if you have non-disjoint events in your probability distribution, you're going to end up with a probability that's more than 1 total. And each probability must be between 0 and 1. Alright, so for 2 tosses of a coin, your events are heads, 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 tails, 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 or tails, heads, and you have a 0.25 probability of each of them. And so, checking off the rules, the events are disjoint, each probability is between 0 and 1, and if we add all the probabilities up, they add up to 1. If you do these in terms of percents, you can have your probabilities in terms of percents, and that's totally fine. It's just that they're going to add up to 100% instead of adding up to 1. But it's the same thing. In a survey, 52% of the respondents said that they're Democrats. What is the probability that a randomly selected respondent from this sample is a Republican? We cannot calculate that. We can calculate the probability that they are not a Democrat, but we don't know the probability that they are a Republican because we don't know if the sample contains people that are only Republican and Democrat, or if there are some people who are not a part of a political party or are part of some third party, right? So if the only two options are Republican and Democrat, you have answer choice A. This is actually going to be the probability of DC, right? The complement of the people who are Democrats. It cannot be more than 48%, but it could be less than 48% if the probability of DC does not equal the probability of R. So, a sample space is the collection of all possible outcomes of a trial. So when we do our probability distribution, if we go back here, right? So this is the sample space of all the outcomes of 2 tosses of a coin. This is the sample space for 1 toss of coin. So, sample space, collection of all possible outcomes of a trial. So, coin is tossed once, the sample space is heads or tails. The coin is tossed twice. What's the sample space? You can either have 2 heads, heads, tails, 2 tails, or tails, heads. Complementary events, we talked about. 2 mutually exclusive events whose probabilities add up to 1. So, event E and event not E. Alright, coin is tossed once. If we know the toss is not heads, what is the outcome? Alright, so the complement of heads is tails, because there's only 2 outcomes when you toss a coin. Right? Heads and tails are complementary outcomes. A coin is tossed twice. If we know the outcomes are not the same, what are the possible outcomes? Right? So your possible outcomes, if we eliminate the ones that are the same, we get the complement, which is 2 outcomes that are not the same. Heads, tails, and tails, heads. Two processes are independent if knowing the outcome of one provides no useful information about the outcome of the other. So, coin tosses are independent. Knowing that the coin landed on a head on the first toss does not provide any useful information for determining what the coin will land on the second toss. Knowing that the first card drawn from a deck is an ace does provide useful information for determining the probability of drawing an ace on the second draw if we don't put the first ace back. If we put the ace back, then they're independent events. But if we don't put the ace back, then they are dependent. So, drawing things from, drawing cards from a deck, drawing marbles out of a bag, without replacement, those are dependent events. With replacement, they are independent. And so this concept of independent and dependent is going to be really important. A lot of times we are going to be assuming that events are independent, even if maybe really technically they're dependent, because it makes things a little bit harder if they're dependent. Probabilities of independent events are super easy to calculate. Between January 9th and 12th in 2013, Survey USA interviewed a random sample of 500 North Carolina residents, asking them whether they think widespread gun ownership protects law-abiding citizens from crime or makes society more dangerous. 58% of all respondents said it protects citizens. 67% of white respondents, 28% of black respondents, and 64% of Hispanic respondents shared this view. Which of the following is true? Right? So, they're not complementary, right? Because gun ownership and race don't add up to 1. They're not mutually exclusive, and therefore they are not disjoint. They are dependent. Why are they dependent? Well, if they were independent, if they weren't correlated at all, what would you expect the probabilities when you break down by race to be? You would expect them to all be 58%, right? 58% of each racial category would say that gun ownership protects citizens. The fact that it differs by race means that the two events are dependent. So, multiplication rule. For independent events, the intersection of two independent events, A and B, we multiply those probabilities. And we can expand this to any number of independent events. It doesn't just have to be 2. We just keep multiplying the probabilities. Right? You toss a coin twice. What's the probability of getting 2 tails in a row? These are independent events, so the probability of the first toss being tails is 1/2. And the probability of the second toss being tails is 1/2. You multiply those, probability of getting 2 tails is 1/4. Which makes sense when we look at the sample space, right? The sample space for 2 tosses of a coin, we said, are heads, 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 tails, tails, heads, and tails, tails. Your probability of getting 2 tails is 1 out of 4. A recent Gallup poll selects that 25.5% of Texans do not have health insurance as of June 2012. Assuming that the uninsured rate stayed constant, what is the probability that 2 randomly selected Texans are both uninsured? So, here's the thing with the independent versus dependent. If we select one random Texan and then we don't put them back, the probability of selecting another random Texan that doesn't have health insurance is slightly different. Because we take out one uninsured person, there's a slightly different number of uninsured people out of the total. Our total goes down by 1, and our number of uninsured people goes down by 1, because we took out one uninsured person. So, to be entirely accurate, we would treat these as dependent events, but that's a lot of work. And there are so many people who live in Texas that the difference is going to be very, very slight. So, we're going to treat these as independent events, even though technically they're not. In order for them to be independent, you would have to have the probability of getting the same person twice. But we're going to pretend like they're independent. So we're making an assumption that these events are independent. If you're using this rule, you have to know or reasonably assume that your events are independent. So, anyways, assuming that both of them, that these events are independent, probability of 2 randomly selected uninsured Texans is going to be the probability of 1 Texan is uninsured squared, right? 25.5% is 0.255, same probability for both, so you multiply those together. The sum probabilities of 2 disjoint events always add up to 1? Not necessarily. There may be more than 2 events in a sample space. So with our party affiliation, right? Democrat and Republican are disjoint events, but there may be other parties that one could be affiliated with. So, two disjoint events are not necessarily complementary. Two complementary events, probabilities do always add up to 1 because that is what complementary means. So, again, if our probability of being uninsured in Texas is 0.255, if we were to randomly select 5 Texans, what is the probability that at least one is uninsured? Right? So, if we were randomly select 5 Texans, the sample space for the number of Texans who are uninsured is 0, 1, 2, 3, 4, or 5. And so we want the instances where at least one person is uninsured, which is the 1, 2, 3, 4, 5. Now we could calculate these probabilities individually. When we talk about binomial distributions, that's a thing that you can do. We can calculate the probability that exactly 1 out of 5 Texans is uninsured, and exactly 2 out of 5, and exactly 3 out of 5, and exactly 4 out of 5, and exactly 5 out of 5. But that's a lot of work. That's so much work. Instead, divide the sample space up, kind of reframe things. Divide the sample space up into 0 or at least 1. So then the probability of at least one uninsured person is 1 minus the probability of none. Right? So, probability of at least 1 plus probability of at least 1 complement equals 1. And at least 1 complement is none. Not at least 1, which would be none. So, you can solve for the probability of at least 1, and you would get 1 minus the probability of none. And that is a lot easier because you only have to calculate one probability instead of 5. So, our probability that none of them are none uninsured. Right? Probability that at least one is uninsured is 1 minus the probability that none are uninsured. Or, that is to say, that everyone is insured. So, the probability of being insured is 0.745. Right? If the probability of being uninsured is 0.255, the probability of being insured is 0.745 because they're complements. For 5 people, we use that multiplication rule. We multiply that 5 times. That's the probability that everyone selected is insured. None of them are uninsured. And then we subtract that from 1 to get the probability that at least one is uninsured. Which ends up being 77%. So, this is the important thing. Probability at least one person, or at least one of anything, is 1 minus the probability of none. It's very handy. Please remember that. Roughly 20% of undergraduates at a university are vegetarian or vegan. What is the probability that, among a random sample of 3 undergraduates, at least one is vegetarian or vegan? The probability of being vegetarian or vegan is 20%. Probability that at least one person is a vegetarian or vegan is 1 minus the probability that none of them are. The probability of being not vegetarian or vegan is 1 minus the probability of being vegetarian or vegan, which is which is 20%, so 1 minus 0.2 equals 0.8. Probability that out of 3, none of them are vegetarian or vegan is going to be 0.8 to the third. So probability the first one is not, times the probability the second one is not, times the probability the third one is not. The probability of at least one then is 1 minus 0.8 to the third. And my little Halloween joke. This is a normal distribution, and this is a paranormal distribution. I'll pretend like you're laughing. Anyways, that's it for our basic probability rules. Next time we get to talk about conditional probability, which is when we make things harder. It'll be a fun time.